Hey, welcome everybody to Every Day Asphalt. My name is Jim Warren. I am with TechSAPA. We are glad to have you guys here today. This program goes a little bit deeper in the areas of materials, design, construction, and maintenance. And it's really important that we understand the interrelationship between all these programs. And so we're taking our engineering class, which is available online, and taking these programs, which meets every Thursday or every third Thursday of the month at 3 o'clock, and we're going a little bit deeper. So today's program, we're going to go a little bit deeper on pavement design. And the other thing is we take these programs, and we're broadcasting today this program, but we also take these programs, we record them, and we will put them up on our YouTube website. Our YouTube website, if you go to YouTube, everybody knows where it is. Type in Texas Asphalt Pavement Association and you click right down here in the bottom here and you can see our playlist for Every Day Asphalt. We've got all of our programs in there for this year. And we'd also like you to, if you're not doing it, there we go, I hit the wrong button, go over here and like, subscribe, and share, so then you will be notified when we place up a new product up on their website, whether it's a program like this, or we also have podcasts and other things that we put up on the program. So excited to have you guys here. Lots of opportunities to share information. So today, our special guest is Dr. David Timm. He's with Auburn University. Let me bring David in here. David, good afternoon. How are you?
Hey, Jim. Doing good. Glad to be here.
Man, every time I talk to David, I learn something. So this is really cool for me today to be able to do this. And David has been a stalwart there at Auburn University. David, just for people who may not know you, because I mean, this is a kind of a Texas program, and a lot of people know everybody from Texas. But what's your background? Where are you from? Where did you grow up? Where did you go to school? How long you been at Auburn? That sort of stuff.
Sure, yeah. So I'm originally a Midwesterner. I grew up in Wisconsin, and then
you're a cheesehead, huh?
I'm a cheesehead, proud cheesehead, absolutely. And then went to school in Minnesota. So I crossed the border and became a Golden Gopher.
Okay.
For about 10 years, I was living in Minneapolis, St. Paul area, going to school. I got my undergraduate, master's, and doctoral degrees.
Wow. Okay. Okay.
And while I was there, I met a Texan named Dave Newcomb, and he lured me into the asphalt business and promised me, fame and riches. And neither of those things panned out too well, but it's been a really fun career. And so while I was in Minnesota, Minroad had just gotten started, and a full scale. It's on I-94, full scale pavement test facility that MnDOT operates, and I got to work with that facility. And then when I was finishing up looking for jobs, Auburn had an opening, and Auburn being the home of NCAT, there wasn't a better place, in my opinion, to land coming right out of grad school than to come here to Auburn. And
Gotcha.
The test track had just opened, and so I got to come here, and I've been here since 2001.
Okay.
So 22 years later, 6 or 7 test cycles later at the test track, and it's been a lot of fun and getting to work in academia, but we have such strong ties to the industry, with NAPA and all the state associations.
Yeah.
That's been really one of the best parts of my job, is all the interactions we get to have with the paving industry. It's really been awesome.
Got it. So what's your specific area?
So so the bulk of my time is spent on full-scale accelerated asphalt pavement testing. So much of that is at the test track.
Mm-hmm.
And what I really specialize in is in thickness design systems.
Okay.
And whether that's improving our older systems, and I'll be talking about that a little bit in the webinar, or the technical content, or developing new pavement systems or ideas to go into those systems. And again, the focus today, I'll be getting into some of the stuff that came out of the test track that has wound up into perpetual pavement design systems.
Yeah, so for the folks that don't know, NCAT stands for the National Center for Asphalt Technology, right? And they've been around since the late 90s, when they really got started. And they have built a 1.7 mile oval track, and it's got a bunch of different test sections from states and different people or different organizations that they build, and they run traffic on that for 3 years. Is that right, thereabouts?
It's 2 years, and then we have a year where we do forensics and reconstruction.
So they put 10 million easels on the pavement in each cycle. Okay, and some people leave things in for different cycles, and Texas has got a number of sections in there, and they've left sections in there to see how long they go. And so it's a really great, it's not on the interstate, but they monitor the traffic. They know exactly what the loads are. It's really tightly regimented, and every week, if I'm not mistaken, they used to, but every week they go out and they monitor the performance of the track. So now you have performance curves as the pavement gets additional traffic. So it's what, 5 days a week or 6 days a week of trafficking?
They're running 16 hours a day. There's 2 shifts of drivers, 16 hours a day, and they're running basically five days a week.
Okay.
And as a team, there's 2 shifts of drivers. As a team, they put about 1 million laps into the track every 2 years.
Wow.
So it's a study in human fatigue.
I was going to say, he's turning left.
A lot of left turns, a lot of diesel fuel. But we have an opportunity to make a big impact in the industry.
Sure.
Think about various things that we're able to do to study, and then work that into state specifications, and maybe open up a specification that formerly was restrictive, that we show at the track that whatever it was that was prohibited, now you can use. And we're doing a lot of cool stuff at the track.
That's good, and it's neat because it's off system, so you can try stuff, and I think a lot of times if you look at some of the reports, this failed or that failed, it's like, you design them to fail. Okay, you design stuff to actually show distress, so you can figure out where the limits are, and I think that's one of the things we're going to talk about today. As we go through this. So, hey, great intro. Great seeing you again, even though it's not in person. I did see Dr. Newcomb with Dr. Epps the other day. They were in town here.
Yeah.
And so David's still doing great, and I will pass on. I didn't know the relationship, so that's good to know.
Yeah.
Just to let you know, I delivered the first pickup truck for NCAT when they got started. So I go way back.
That is a while ago.
I go way
at the track somewhere.
I go way. Yeah, it's probably buried in the track. All right.
Yeah.
Well, good deal. All right. So what we're going to do, ladies and gentlemen, is we're going to switch gears now, and so David's going to go full screen with his presentation. Normally, I kind of talk through it with our presenters, but this time we're just going to let David do his presentation, and then I'll come back at the end. And like I said, I got questions. So we'll pick that up on the other side. So David, are you ready to go ahead and do your piece?
Yeah, let's do it.
All right, so we're going to go ahead and switch over, and then we'll be back as soon as he gets done. So hang on here just for a second.
Thank you again for tuning into this webinar. And as we've been discussing, today I'll be digging into some of the ideas of using perpetual pavement concepts to arrive at maximum pavement thickness. And a lot of what I'll be presenting comes from the NCAT Pavement Test Track. Before I start talking about perpetual pavements, I just want to provide an overview of where we've been and where we're going in terms of structural pavement design for flexible pavements. And really before the 1950s, it was really experience-based. You had local engineers, usually geotechnical engineers, that knew their materials, the traffic and the soils and so on. And they were able to come up with pavement thicknesses pretty reliably under relatively low traffic demands. However, as we advanced into the 1960s, we had the rise of the interstate system and much more freight being carried over our highways. And there was a need to have a more robust design system. And this is what led to the development of empirical pavement design methods in the 1960s. Jump forward into the 1980s, and there was a realization among pavement engineers that we needed an even more robust and more adaptable design system. And this is where the first mechanistic-empirical methods were proposed. And the problem that we had in the 1980s is that we had the ideas, but not the computational power. It required supercomputers in order to do the computations needed to do this type of design, this mechanistic-empirical pavement design. And so it really had to be put on the back burner until we got into the 1990s when the computing power caught up with it. And then we had NCHRP 137A, a big national project, that the main objective was to develop the next generation of pavement thickness design for AASHTO, and at that time it was called the AASHTO 2002 Design Guide. and is now called the MEPDG, or Mechanistic-Empirical Pavement Design Guide. And it really ushered in the era of ME design. And many states are currently grappling with how best to implement ME design. And that's really where we are now in the 2020s now, is implementing ME methods. Most state DOTs are either they have implemented or they're doing studies to help them implement ME design. And as a subset of ME design, we now have perpetual pavements, and that's really the focus of what we'll be looking at. So where we are today, as you look across the U.S., is that we have a variety of empirical or mechanistic empirical approaches that are in use. The goal of any design system is to optimize the thickness for the prevailing conditions, the traffic, the environment, and so on, the materials that you have at hand. And calibration of those design systems is really critical. You might have heard about calibrating mechanistic empirical design or calibration studies, and all of that is geared around making sure that your design system accurately predicts the performance of the pavement so that you can come up with optimized, as it says here, optimized pavement cross sections. Most of these design systems, or many or most of them, do not check at the end for maximum pavement thickness. It's really up to the engineer. Maybe there's a policy decision that has been made somewhere, written down somewhere, but most of them do not have built into the system a check for maximum pavement thickness. So if you're running the old AASHTO 93 or running a mechanistic empirical approach, as you continue to add traffic or have higher and higher traffic levels in that design, it'll recommend or require greater and greater pavement thicknesses, and that can quickly lead you into a situation where you have overly thick asphalt pavements. And what's shown in the picture here on the right is a core that we cut out. We had an experimental program going on in partnership a number of years ago with a provincial government in China. And they have extremely heavy trucks, and we developed a perpetual pavement experiment, or helped them develop and deploy an experiment there. And this is one of the 5 sections that we build a core cut from it. And this is 20 inches of asphalt. And under most conditions in the U.S., that is going to easily meet any metric for perpetual pavements. In China, this is what was required to handle that kind of traffic, but it performed well and was able to clearly demonstrate that if you can properly consider traffic, environment, materials, and all that, and put it all together and look at perpetual pavement concepts, you can arrive at a pavement cross section. Again, this would be way too thick for most traffic conditions here in the U.S. To demonstrate this idea that more traffic means more pavement thickness, let's look at the simple example that comes from the AASHTO 93 design guide. What I've got in this plot is AC thickness on the vertical scale, so the required pavement thickness, versus the traffic level characterized by millions of easels. And keeping all else constant, you can see that in this framework, in this design framework, which many states use, that as we continue to increase traffic, we have a continued increase in the pavement thickness, and there really is no upper limit to it. The change, or the rate of change, may decrease. It may start to level out, but it just continues on. And we can, in some urban high traffic environments, we can quickly get to traffic levels that are in this order of magnitude: 50 million easel, 100 million easel, 200 million easel. And the sad truth of it is there's no natural upper bound to this, according to AASHTO 93, other than what engineering judgment or policy decisions may be made within a local agency. And so the idea is, with perpetual pavement concepts, is that somewhere along this curve there ought to be a maximum pavement thickness. We need to know where it is, so that once we get above that or to that point, we don't need to continue to add thickness to the design. We need to be paving further rather than deeper to make the best use of our resources. So really the underlying question to all of this is, how thick is thick enough, and how do we figure that out? And perpetual pavements are the key to understanding and coming up with how thick is thick enough. So what does a perpetual pavement look like? And in 2001, Dave Newcomb published this figure, and it really does a good job of tying together a lot of the key concepts and ideas going into a perpetual pavement. Remember that a perpetual pavement is one that does not have deep structural distresses, meaning bottom-up cracking, that cracks that initiate and propagate to the surface of the asphalt, and we don't have deep structural rutting. So it all begins by focusing our attention on a strong pavement foundation that considers drainage. On top of that, we have these various materials, and we're selecting high-quality rut-resistant materials in the middle and upper layers to combat rutting of the AC mixture. And then down towards the bottom of the pavement, we need to think about the fatigue resistance, the cracking resistance of that material, because if we do a good job of that, and we build it just thick enough, we're not going to have enough tension occurring at the bottom of the asphalt to initiate and propagate a crack to the surface of the pavement. So how do we achieve that in terms of thicknesses? Over here we have some typical depths, and it's very interesting that these are not overly thick. If we think about and look at the, say, the minimum thicknesses, we arrive at about 8.5 inches total here, and on the high side about 14. And you'll see in my following slides and some information that I'll be presenting in just a minute that what we see in the real world are exactly this. We're not looking at 20-inch pavements to achieve perpetual. We're looking at something in that about 8 to 14-inch range gets us there in terms of a maximum pavement thickness. So how do we come up with a specific set of thicknesses for the design conditions on a case-by-case basis? And that's best handled through mechanistic-empirical pavement design. And perpetual pavements is a subset of that. So let's start with ME design, and then we'll do ME perpetual design. So ME design begins by coming up with a set of pavement thicknesses. We have to guess at what those ought to be, and also characterize the material properties alongside that. So say the layer moduli of each pavement layer within the pavement system. We then simulate a loading event on the pavement surface and use a mechanistic model. So this is the M part of ME design. We use a mechanistic model to calculate a critical pavement response. And then we have an empirical relationship that links the mechanistic response to an empirical prediction of performance. And so we know we have a certain amount of strain happening in the pavement under this set of conditions. And then the prediction is made empirically about how much cracking we're going to see. And we can do that for bottom-up cracking. We can also do that by looking at deeper in the structure at the pavement responses there and make a prediction about how much rutting we might see. And so that's the two parts. The mechanistic is all the layer property, material property, load event, and so on to get us to a prediction of how much stress or strain we see. And then the empirical part is that empirical link to take that stress or strain and then predict performance from it. Perpetual design has many of the same elements. We still characterize the layer thicknesses and the layer properties. We look at load events, very specific load events in terms of load magnitude. We calculate pavement responses, but now instead of making an empirical prediction of performance, we're trying to limit how much strain we see to some critical level. We call it the threshold strain or the endurance limit. And if we keep the strain level that we see in the pavement below the endurance limit, there will never be enough, say, tension at the bottom of the asphalt there to propagate or initiate or propagate a crack to the surface. That's where we want to be in terms of perpetual design. And likewise, we can think about deeper in the structure and limiting to some endurance limit, limiting how much strain we see there so we do not see those types of distresses at the top of the pavement. So that characterizing that endurance limit is very important in perpetual design. So given the importance of the endurance limit, you may be wondering, well, how do you measure it? Where does it come from? And one of the ways we can come up with an endurance limit is to measure it in the laboratory. We can take an asphalt concrete beam like this and stick it in a bending beam apparatus like that, subjects it to repeated flexure, generates tension at the bottom. And we do that at a certain strain level, and we repeat it over and over and over again and count up the number of cycles, which is on this axis, the number of cycles until the beam fails. And we normally do that over a range of strain levels. So at the higher levels, more bending, we generate relatively few number of cycles to failure, and then we drop the strain level a little bit, we get more cycles. We do that a number of times, and we eventually see a trend to emerge where we can link up the strain to the number of cycles to failure. And this is when I talked earlier about the empirical part of ME design. This is what we're talking about, is a link between a mechanistic response like tensile strain and an empirical performance prediction like the number of cycles until it fails. And this type of testing has been done since the 1960s. There's lots of studies have been done over the years, and they all have mostly in common that you do it over a range of strain levels, and then you fit a curve to that data set and you just extrapolate it down and you extrapolate it up. But what that ignores is the fact that most materials, and asphalt concrete included, have an endurance limit, a strain level below which you will not induce damage. And if you run this type of test and you run it at a low enough strain level, what you find is that it doesn't continue down. It actually starts to reach an asymptote here. It starts to level off. And for most asphalt concrete materials, that number is, as a minimum value, is around 100 microstrain. So you can, for most modern asphalt concrete materials, 100 microstrain is a pretty safe bet. And we call that the endurance limit, and that is defined as the threshold response below which damage does not occur. So if we're designing the pavement and we know it can handle up to 100 microstrain before it would crack, we design it so that just thick enough so that we're below that 100 microstrain limit. If we're below the endurance limit, we do not get bottom-up fatigue cracking in that pavement. So that's how we come up with it in a laboratory. And that type of testing is done at a particular temperature, a particular frequency. And though it's meant to replicate field conditions, it doesn't really replicate real world conditions. In the real world, the pavement is experiencing a wide range of loadings, wide range of environmental conditions. It's perhaps aging over time. And so rather than just having a single strain level, it may experience a whole range of strain levels. And what this plot is showing is data from our NCAT Test Track. And what it's representing here is the range of strain levels, that tensile strain that has been measured inside of the pavement section of the test track. In some of our sections, we instrument them so we can make measurements of strain. So rather than predict it, we just measure it directly under traffic. So this is the range of strain levels, and then this is the cumulative percentile. So up here, this is the maximum strain that these sections saw. Down here, the 0% is the minimum. Say the average or the mean value of strain that was measured across all of these different pavement cross sections. And they represent different types of materials, different soil conditions, and so on at the test track. And what was really interesting when you first look at a plot like this is it looks like a jumble of curves, and you have some that have high strain, some that have relatively low strain, and then everything in between. And it doesn't have a whole lot of meaning until you know what the cracking history of these sections was. And what we found when we look at this family of curves is that everything on or to the left of this blue curve did not experience bottom-up fatigue cracking. You have a couple that are right on it. You have some that are further away, meaning they had lower strain. And then you even have one that's way over here. It almost looks like tick marks on this vertical scale. This is actually one of the original test sections at the test track that was 2 feet thick of asphalt, had extremely low strain levels, and was designed purposely not to have bottom-up fatigue cracking because of the objectives of that first test track experiment. And it's like super conservative. And then you have things that are a lot less conservative, but every one of these sections did not experience bottom-up fatigue cracking. Conversely, everything on or to the right of this red curve did experience bottom-up fatigue cracking. And then we have a gap between these two. And then down below here, the lines start to cross and so on. But in putting this data set together, what we came to realize is that rather than design for a single strain level, like what comes out of the laboratory, what if we design for a distribution of strain? And that's where this blue curve comes in. This is like a curve that we can use to help us design a perpetual pavement or come up with a maximum pavement thickness, as I'll show you in just a minute. And then the further we go to the left of that curve, the more conservative it is, and the closer we are to the curve, the less conservative it is. And what's interesting is these all came from the test track. So this curve here essentially was about 9 inches of asphalt on a pretty good pavement foundation. This section was 24 inches of asphalt on essentially the same pavement foundation. There's 15 inches of pavement thickness between this curve and that curve. All of this is over design, and like I said earlier, we could pave it further rather than deeper and still achieve the same performance. These two sections had the same performance essentially, and this is arrived at through over design. This retrospectively is achieved through optimized design. So that's what we found at the test track. What about the real world? And what this graph is showing is where we did a validation study to look at Perpetual Pavement Award winners. There's an awards program that identifies and recognizes pavement sections all over the country that meet Perpetual Pavement criteria in terms of performance. And this is just a relatively small sample of those pavement sections that we use for this investigation. The red line is indicating the total depth of asphalt concrete thickness. So within this range or this group of sections, and they come from various states, but the thickest section came in at 21.5 inches, again, probably achieved through over design when it was first built over 35 years ago. And then the thinnest section we had in this group was about 7.5 inches, and they represent a range of soil conditions, base, subbase, and so on. So we have a range of pavement sections, and the question that we asked was, if we apply the criteria that came from the test track to these sections, does it predict that they would be perpetual? And that is shown here on this slide, where we have the criteria from the test track. That's this black line. And then all the sections that were simulated here, that's all these different series, and every single one of them fell to the left, to the good side or to the perpetual side of this endurance limit curve, if you want to call it that. So yes, we were able to validate that. You can look at, just like the other sections from the test track, some are less conservative, like Montana being the thinnest of the sections there. That came closest, but didn't cross it. If we look at the thickest section, Iowa, that was the 21.5-inch section. You might guess that, yeah, that would probably be pretty conservative, and compared to the criteria, it definitely was. And then we had everything in between. Again, these were all pre-existing old pavement sections that met perpetual pavement criteria in terms of performance, and every one of them passed that. And so that gives us a lot of confidence that we can use a curve like this moving forward to design and analyze perpetual pavements and come up with maximum pavement thicknesses. So that validates the criteria for fatigue cracking. What about rutting? Well, if you read in the literature and you look at research that's been done in this area, most people, or there seems to be some agreement, that we need to look at 200 microstrain vertical compression down inside of the subgrade and control that on average, so at the 50th percentile, for example. And so we took those same test sections that I was just talking about, simulated them, and what we found was that every one of them, the one that came closest was in Kentucky here, every one of them was below the 200 microstrain criteria. And so we felt like that was a good validation, and using that, it seems to give us some pretty reasonable cross sections as well. And so we have both for bottom-up fatigue and deep structural rutting now criteria that were developed at the test track and then proven by looking at real-world perpetual pavement cross-sections. The concepts that I've just been describing are embedded within a few different design tools that are freely available. You can find these online. You can scan the QR code there on the left to get to PerRoad and PerRoad Express, and then the program on the right is actually runs within a web browser called Pave Express. And if you put that keyword into a web browser or into a search engine, you will quickly find it. But they are free to use. They were developed for the industry, and they utilize the concepts of using strain distributions and so on to generate pavement thickness. And you can use them to come up with maximum pavement thickness. So it's another tool in your toolkit. If you're doing design and you have some officially approved design system, Astro 93, AstroWare Pavement ME software, something like that, or TexME or some other program, you can use these tools as just another way to look at the pavement cross-section and see what it's telling you in terms of pavement thickness. Once we had the concepts worked out and the software developed to where we could use it to do some what-if type scenarios, we were able to do a study, and this particular one was led by one of our NCAT research professors, Dr. Nam Tran. He led this investigation. What we did is we looked at a variety of support conditions, different foundation conditions, from relatively soft to relatively stiff, and then varied the base stiffness, the aggregate base, from, again, relatively soft to stiff. Looked at a few different climate zones, from cold to desert to more moderate, like we have here in Alabama. And then we tried out different base thicknesses. So for example, we see base here, 6-inch aggregate base. We're changing the modulus of the base here over a range of conditions. And you can see the thicknesses that we came up with. And I just want to focus in over here the range of thicknesses. So on the low end, over a wide range of conditions, we had 8 inches thick. And on the thick end, for the softest conditions here for the foundation, we came up with 15.5. And if you remember back to that first graphic that I showed you from Dave Newcomb, he had it around 8.5 to 14. What we found here over a much, that was a typical cross section. It's a little bit wider. We're 8 to 15.5. But we're definitely still in that same order magnitude range. We're not talking about 20-inch pavement sections. We're not talking about 3 or 4-inch pavement sections either. We're in that range of about 8 to about 15.5 in this particular case. If we look at a 10-inch aggregate base, again, same set of conditions here. The thicknesses come down a little bit because we have more aggregate base. There's more pavement structure underneath the asphalt. Now the thicknesses drop. We're down around 6.5 up to about 14.5. But again, we have a working range. And from from an implementation standpoint, tables like this are really useful because you don't have to go through and use all the software and everything. You can kind of look at, okay, I'm in this type of climate with this type of soil and so on. And if I'm getting something north of 14, 15 inches based on this table, I probably am designing it too thick, and I maybe should do some more investigation of it. I should also point out that using strain distributions and per road or Pave Express aren't the only way to go about coming up with maximum pavement thickness. The Illinois DOT has had for a long time in their design code an approach that essentially you do a conventional pavement design and then you check it against a map like this to look at what is the recommended maximum pavement thickness, and if you exceed that, then it's capped. And their approach is quite a bit simpler and more straightforward than using per road or Pave Express. They look at the hottest month, the heaviest design load here. They use an axle load of 20,000 pounds. The hottest month they use July. They have some other assumptions in there. They use a pretty conservative strain level. And essentially they've gone through and done the computations, and the further north you are, the relatively thinner it is in terms of maximum thickness. And as you move further south, the thicker it gets, and that's taking into account some climate changes as you go north-south through the state. But they have, in terms of implementation, a really simple, straightforward way of doing this. And again, if your project is in the middle of the state and you're coming up with 17 inches, well, then you're probably too thick and you need to adjust that down a little bit. They've been using this for a long time and have a lot of confidence in using it. So whether you're using a per road approach with strain distributions or something like the Illinois approach that I just showed, the application of it is essentially the same. And this graph is what I showed earlier in terms of the blue curve here, where we have increasing pavement thickness with increasing easels. But then I've superimposed over the top a perpetual pavement thickness, a maximum pavement thickness using those concepts. And you notice that it's fixed. Traffic volume doesn't matter with perpetual pavements. What matters is how heavy the trucks are. That's the primary driving factor. That maximum thickness is fixed. And so even when we're way out here, 100 million easels, as this one continues to increase, this is simply capped. And at some point they cross. And this is just a particular example, so don't read too much into that. At about 12.5 inches is what this maximum thickness is. But you can imagine that in a hybrid approach, we do a conventional design, but only up until we hit that maximum thickness, and then the maximum thickness takes over. And again, that might shift up or down depending on the prevailing conditions where they cross. But in this example, they crossed at about 12.5 inches. And as we go further to the right here, we have greater and greater savings in terms of material construction and overall costs and so on. So this is a key concept with perpetual pavements, is we can use it in a hybrid approach to just make sure that we're not over-designing and overbuilding our pavement infrastructure. So to wrap up, I just want to close by saying that most modern pavement thickness design systems aren't checking for maximum pavement thickness. You may have a strong suspicion that it's over-designed and going to perhaps be overbuilt, but most of the systems, unless you have some policy document or something like that, don't automatically check for that maximum thickness. The perpetual pavement concepts that I have presented here today are proven. We have lots of perpetual pavement award winners from around the country. These things exist. There's lots of data about them, and using that data is where these concepts come from. And we can use those concepts to generate a maximum pavement thickness over a wide range of conditions. It doesn't matter where you are. There's a system that you can follow to arrive at a maximum pavement thickness. If you use perpetual pavement in conjunction with conventional design, that can help you achieve more efficient pavement sections and keep you away from getting these overly thick pavement cross sections. And finally, and I believe strongly in this, designer-friendly deployment is important. Having to run really complicated design simulations can be an impediment to implementing this type of thing. Having tables like I showed, or having a simple contour map that shows what the maximum pavement thickness is in your area, I think is a really effective way to go about implementing these types of ideas. And so with that, I'll just show you a couple of references. If you're interested, you can find these online very easily. If you go to our NCAT website, ncat.us, you can find some of our reports, and this one in particular that talks about these maximum thickness ideas. And so with that, I'm going to wrap up and thank you again for your attention. And I think we're going to have a little more discussion. Thank you.
All right, we are back with David Timm. A great presentation, David. A lot of great stuff in there. I had a couple questions, if you don't mind. You know, one of the things that's really interesting about that is, you know, we think about the traditional, the load repetitions and that kind of stuff, and eventually stuff's going to fail, right? And I think that's the thing that we learned about perpetual pavements and that kind of stuff, and the stuff we learned today, is that if you don't overstrain that stuff, it's not going to fail. So we really can build these pavements that are going to last essentially forever, which is, I think, a really, you know, from an engineering standpoint and from an economic standpoint and a sustainability standpoint, that's you know, that's a home run. You know, that's a, you know, grand slam, if you know. Thoughts?
Yeah, so I agree 100%, obviously, with everything you just said. And what's really, to me, is interesting, right? As pavement engineers, we're trained to, you know, we're designing for ultimate failure, right?
Right.
Using the old Astro 93, we say, okay, it's gonna tail off over time, and we design it to fail. Or in Mechanistic-Empirical, we say, okay, after 20 years, we're gonna have 25% cracking. We've got to go out and tear it up and repair it and everything. We don't design any other civil infrastructure like that. We don't design a bridge to collapse in 20 years.
Well, that's a good thing.
And so, yeah, exactly. And so, and central to all the designing all those other things, foundations, buildings, bridges, whatever it is, they're designed with an endurance limit in mind, right? Or a threshold in mind. If you think about steel design, right? We know what the limit of that steel is, and then we size the members to be, to provide, stress and strain that we're below that limit, right? And then unless it's a catastrophic event, is going to be there for a very long time.
So you're moving the cheese here, right? You're moving kind of the conventional, since you're from Wisconsin, you're conventionally moving the cheese away from a kind of an old school way of doing things, which has worked. I mean, it's worked for a long time, and I think by default sometimes we built perpetual pavements. Not necessarily by design, but kind of by, you know,
by over-design.
By over-design, sure. Yeah. But I think as we move forward with this, and I think you had a slide in there, where was that? You had a graph of easels versus AC thickness, right? And the first one, based on the old Astral design, kind of went up and up and up, and we were seeing thicknesses at some of the levels that we're seeing pavement traffic now, 80, 90, 100 million easels of up to being over 20 inches thick. But with your application of the perpetual concepts and that limiting strain or concepts, you know, the asphalt thickness is maybe, you know, 12, 13, 14 inches thick.
That's right.
Which is, I mean, again, economics, sustainability, reliability, and you got the math, you know, with the real life projects to show that this stuff actually works. I think that's really cool.
Yeah. Oh, yeah, absolutely. And I think one of the central things, and I think I, you know, talk about it during the presentation, but I'll emphasize it again based on what you just brought up, is that, you know, once you get to a certain thickness, the volume really doesn't matter anymore. What matters is how heavy those trucks are. And if you've built it just thick enough that that there's just not enough bending going on, just like in the laboratory, if you're doing a fatigue test, you can flex that thing a million times. It's never going to break. But if you get it to a certain point, it may. And so knowing where that is and designing it just thick enough with the right materials and doing a good job, all the things that we know how to do well, do all that correctly, get it just thick enough, and then the traffic volume really is a non-factor. What matters is how heavy those trucks are.
So if we, okay, let's just, I know it wasn't part of your presentation, but since you mentioned that, so as we get heavier, there's already, you know, there's already been, you know, we've seen efforts just recently of saying, hey, well, the electric trucks need to have a higher gross vehicle load because they're carrying all the batteries. So we need to go from 80 to 80 something, you know. And so we know as we increase the load, we increase the damage potential, right? So is this going to be capable of adapting to that system as we change loads?
Absolutely.
Okay.
Yep. Okay. 100%. So what we once we've characterized, call it the strength of the material, or fatigue resistance of the material. Once we know where that is, it's just a matter of feeding the loads into the design system.
Okay.
And if they're heavier loads, then it's going to require thickness to increase a certain amount, right? And it's going to be a function of how heavy those axles are.
Gotcha.
That's right.
Gotcha. And you mentioned per road. And I know per road is something that's near and dear to your heart. You've been involved in it. Did you write it?
So it was a collaboration.
Yeah.
So I started working on it when I first got to Auburn.
Yeah.
But it was really Napa funded that. Right. So that it was developed with the support of the industry. And Dave Newcomb, when he was the VP for research at Napa, really got the ball rolling with that. So I would say it was a collaboration between Dave Newcomb, myself, and then a few other people that helped get it going. And
so good. So it's got some.
In terms of coding, I was the primary coder of it.
Okay, so it's got some Texas roots in it, y'all.
Oh, 100%, yeah. In fact, if you really go back further, you can follow that lineage right back to A&M.
Wow. Okay, that's awesome. Yeah. And so. I guess for the folks out there, the designers out there, as we get into these heavier duty pavements, we had recently just had a heavy duty pavement meeting here, which is looking at what we need to do and how we need to condition and get ready for that stuff. And so we're using FPS 21 for TxDOT work right now. We're going to transition to another version, which is a little bit better version of that. It's going to be FPS 23. They've got this TexME system to run a design check on there. But when we get into these really high loads, hey, per road's out there. Okay, it's free. and so there's another design check that you can kind of do the belt and suspenders deal on there, just to kind of give yourself a comfort feel as we're getting into these heavier and heavier loads, just to say, hey, this said this here, this said this here, maybe we're pretty close. Hey, I'm in the ballpark, as opposed to going, God, I hope that works, because we're seeing, with the traffic coming over the borders, and the inland ports that we call them, we've got the sea ports, we've got the energy sector traffic. We're seeing just crazy loads, crazy traffic, way, way beyond what a lot of these pavements were ever designed to carry. And so as Texas continues to grow, we've got to be able to grow with it and build some of these stronger pavements. So there is another group that's working on that here in Texas, from James Stevenson all the way down, and there's going to be more information. There's going to be more training available, probably starting later in the year for these programs. And so stay tuned. We can carry the load. Trying to think if there's anything else in here. Just really good stuff. And again, I think kind of the takeaway is in your summary, and you say perpetual pavements are proven and can be used to generate maximum pavement thicknesses over a wide range of conditions. And I think one of the things that you showed in some of those earlier slides was some of those subgrade strengths were pretty low, right? And and we've got a lot of that here in certain parts of the state, and we got other parts of the state we're essentially building in rock. So we've got that full spectrum of systems that are out there. So really cool. So anything in closing? What else do we need to know? Are we good to go?
Yeah, I think what you described earlier is really a good approach with this, right? Is that there's a variety of design systems out there, and people have different history with different ones, and you have whatever the official one is. But it's it's always good to be checking things with come at it from a few different angles.
Sure.
And most designers that I get to work with and have talked to, they usually know when it's getting to an excessive thickness, but they don't maybe have a tool available to say, well, I ran the computations and this is what it's telling me. And so having tools like this are really important to say, well, I think it's too thick, and here's some data that says, using these criteria, that it is too thick. So instead of 20 inches, 17 is going to do the job. We can pave it that much further for the same cost.
Sure, absolutely.
So I think that's really the takeaway, is to think about paving further, not necessarily deeper.
Okay. Yeah, we need to use the money, and as things wear out, and we gotta rebuild and keep things going forward. So, hey, great discussion. Thank you so much, David, for being with us today on Everyday Asphalt, and we're gonna just kind of wrap it up here. So just remember, these meet every Thursday or every third Thursday at 3 o'clock. If you go to texasasphalt.org, and you can register to sign up to get an email. And once you get on that email, we'll let you know when they're coming up. You can come to any or all of them that you want. But again, we do post those on our YouTube website. Let me go back to there. Maybe. Oh, I lost it. My screen locked up. All right. Well, whatever. And so go to YouTube, type in Texas Asphalt Pavement Association, like and subscribe, go to the playlist, click on Everyday Asphalt, and we'll be there. So in the meantime, please be safe out there. Wear your seat belts, don't drink and drive, don't be distracted and all that sort of stuff. That's a leading cause of fatalities in the state, is those kinds of things. So those things are pretty easy to fix. Just put the phone down and get someone else to drive if you've been having a good happy hour. So in the meantime, take care, everybody. Be safe. We'll see you next time on Everyday Asphalt.